If you've purchased a laptop recently, there is a very high probability it contains a hidden piece of silicon. Right next to the main processor, manufacturers have integrated a specialized third brain into the motherboard that most users never notice. This chip changes the way a PC functions. It allows your computer to handle heavy machine learning tasks locally, moving AI from a distant feature you access over the internet to a capability that lives directly on your hardware. Understanding why this specific architecture was designed is the key to seeing where the next decade of personal computing is headed. Modern software places constant, heavy demands on our machines. We expect laptops to blur our backgrounds on video calls, generate live captions, and run smart assistants in the background without any loss in performance. The traditional central processing unit, or CPU, struggles with these tasks. CPUs are built to execute instructions sequentially, one after another. When forced to juggle the millions of parallel calculations required for a neural network, they often hit a wall, leading to system lag and freezes. While a graphics processing unit, or GPU, can handle parallel math, it functions like a high-performance engine. If you leave a GPU running constantly to power background AI tasks, it will drain a laptop battery in minutes and generate significant heat. This created a gap in computer engineering. Devices needed a way to process continuous AI workloads without the massive power draw that makes mobile computing impossible. The industry responded with the Neural Processing Unit, or NPU. Think of the CPU as a versatile office manager. It is fast and designed to manage sequential tasks, like opening applications and organizing system files. The GPU is the heavy industrial factory. It has the immense scale required for 3D graphics, but it requires significant energy to keep the machinery running. The NPU is a specialist. It lacks the versatility of a CPU, but it can perform specific mathematical operations with far greater efficiency than its neighbors. That efficiency comes down to how AI works. Neural networks rely on matrix math, the constant multiplication of vast grids of numbers. General processors waste energy moving those grids back and forth between main memory and computation cores. The NPU uses direct memory access and on-chip memory to keep data local. It loops those numbers instantly within its internal pathways. Once in place, it feeds into the MAC array, physical hardware hardwired to crunch through these specific grids at high speed. This streamlined memory path allows the NPU to run an AI model continuously in the background without needing to wake up the rest of the system. By tailoring the physical layout to the math, the NPU bypasses the specific memory bottlenecks that limit traditional CPUs and GPUs. Benchmarking confirms this. For low-intensity operations, the CPU is most efficient. For massive data batches, the GPU's raw throughput leads. However, for inference, actually running the model, the red markers show the NPU reaching its peak efficiency. The real-world impact is in the power draw. The NPU can maintain this level of performance while drawing only 35 watts, while a GPU requires 75 watts to achieve similar results. This allows for continuous AI performance while using less than half the peak power of a dedicated graphics card. This hardware breakthrough enables a specific class of laptops to power features like Windows Studio Effects, which handles eye contact correction and voice focus natively. To ensure these local features are responsive, the industry has adopted a new standard. An NPU must hit at least 40 TOPS, or 40 trillion operations per second, to support these advanced functions. Silicon designers at Intel, AMD, and Qualcomm have all pivoted to make the NPU a central part of their processor architecture to meet this 40 TOPS requirement. TOPS is now a primary metric for performance, serving as the standard by which the next generation of mobile computers will be measured. Running a neural network previously required packaging every prompt and image to be processed by a remote server farm in the cloud. Local processing changes that. Because the data stays on your chip, you gain true privacy, zero internet latency, and a much longer battery life. Computers have evolved a specialized new lobe in their architecture. By handling neural processing locally, they have shifted the heavy lifting of machine learning from distant server farms directly onto the device sitting on your desk.